All right, so before we jump into the notes, first an explanation about how your packet is set up so that you know what you're looking at and where to go for stuff. We're going to begin our notes at the beginning, which seems like, yep, that makes sense. But what might not make as much sense at first is that your homework assignments start from the back of the packet and work their way forward. So your homework assignment is the very last pages of the packet today. The reason is because then they're easy to rip off. So your notes start at the front and work their way back, whereas the homework starts at the back and works its way front. So it's easiest to just rip off those back pages each day and hand them in. So we'll kind of work towards the middle of the packet then. Okay. So your homework assignment will be the very last pages of the packet tonight, but our notes start at the front. So in this next unit, what we're going to be looking at are what are called transformations and ways that we can move around two-dimensional figures. We're going to work with two-dimensional figures now, so flat surface plane figures. And today we're going to talk about 4 different ways that we can transform a figure. The first one is called a slide. How it works is it just moves something in a very literal sense. It just picks it up and sets it down somewhere else. Another name for it, the more mathematical, accurate name, is it's called a translation. We need 2 things to be able to perform a slide or a translation, and that is that we need a direction and we need a distance. Or those 2 things are often given by giving an X motion along with a Y motion. And that's how I'll be providing the problems. So as an example, we are going to translate the figure 6, -3. We're going to start with a figure. You don't have to use exactly the same figures that I draw, but it might be best if you do. One important thing to consider when you're creating a transformation problem is that the figure that you're working with should be quite irregular so that we can tell the difference between sides. Like a circle would be horrible to use because a circle looks the same pretty much no matter what you do to it. Squares would be really bad to use. We want there to be a distinction between the sides of the figures. So what I'm going to use give some distinctions between the sides of the figures, either in their length and got a semicircle at one end instead of a straight line. We've got a little peak there so that we can tell the difference between the top and the bottom and the left and the right and so forth. And when we translate, what we're going to do is basically we want to pick this thing up and we want to set it down somewhere new. It should look exactly the same. It should be facing the same direction as it was before. It's just going to be in a new location. And our directions say that we want to translate this figure 6, -3. Those 2 values are giving us an X amount of movement or sideways movement and then a Y movement or an up and down movement. And they come in that order, X, Y, just like algebra, sideways, and then up or down. So what we're going to do is select one distinct point on our figure. It could be any point, but it should be a distinct, easily traceable, markable point. So like corners are a really good thing to do, or you could do kind of the top of that peak if you wanted or something like that. But I'm going to take this bottom corner and I want to take that corner point and I want to move it 6 spaces to the right and 3 spaces downwards. So that point is going to relocate to that new location. 6 spaces to the right and 3 spaces downwards. And then you want to redraw your figure exactly the same. So we're taking this thing and just picking it up and setting it down somewhere new. Faces the same direction, everything's the same size. Questions?
How can you do that with curved line? Like, how can you translate? Because you need points.
Each of the curved points also moves 6 units over and 3 units down.
What's the point of knowing how to do that?
You translate yourself all the time. When you move from this room into another room, you've translated yourself. This is a very important thing in terms of video game design. You're constantly translating figures when you play a video game, any sort of an animated movie. You're translating the characters, and you want the character to look the same in every scene. So we need to make sure that we're keeping the same proportions, the same size of the figure, but just placing it in a new location. Our next kind of transformation we're going to look at is called a turn. How it works is it kind of twists an object. The more mathematically correct name for it is a rotation. We need two things again. We need a point or a center of rotation, and we need an angle. So for an example, I would say rotate the figure 60 degrees. We need a point of rotation, so I'm going to start by just placing a point, and then we need a figure. Again, you don't have to use the same figure I do, but it should be distinct in each of its sides so that we can tell the difference between the right, the left, the up, the down. I'm going to use a puzzle piece as my figure.
Oh, we're supposed to draw.
Well, you don't have
If I can draw it, you can draw it. Thank you. Thank you for the vote of confidence there. But yeah, art is not my thing. And just as a heads up, as we go into this one, this is the most difficult of all the transformations to be able to draw nicely. So, you know, I give a fair amount of grace in your drawings here with the rotations, because the rotations are the most difficult to draw. What we're going to do is select a point on our figure. Again, it should be an easily distinguishable and markable point. I'm going to choose that bottom point. If you have rulers and protractors, they could be helpful in this. If you don't need to go out and buy a ruler or a protractor for what's really going to boil down to like 1 or 2 lessons. But in all actuality, if we wanted to be precise about this, rulers and protractors are actually necessary. We're going to connect that point on our figure to our point of rotation, our center of rotation. We would want to connect that with a straight line. Then what I'm going to do is from that straight line, if I had a protractor, I would measure out a 60-degree angle. If you don't have a protractor, we just want to eyeball what is about 60 degrees. We kind of think of how could I make an equilateral triangle. And 60 degrees, let's see, I think it's going to lay. Well, you could kind of construct a 60 degree, but you'd have to really construct an equilateral triangle to get that 60 degree.
Also, 60.
Yeah. Well, I was thinking about
Don't trust your eyes.
if I had a 90, you know, kind of going 2/3 of the way to my 90.
I think we should use compass.
A protractor would be easier than a compass.
Yeah, it's a big construction.
Then what we want to do is measure the distance from the point on our figure to the point of rotation and mark out that same distance along this new rotated line. Again, you don't need a ruler. You can just kind of take a finger pinch measurement and say, by my fingers, how far is the point on my figure away from the point of the center, and kind of take and turn and mark out, oops, but not with my eraser, mark out that same distance along this other line. And
So this doesn't have to be.
I mean, I'm not going to check your measurements. So, I mean, if we really truly wanted to do this, we would definitely need to be using protractors and rulers. We wanted to have a truly accurate rotation. Then what we need to do is repeat this process for a second point on our figure. So I'm going to choose a second point. Connect, again with a straight line using a straight edge or a ruler, an edge of a sheet of paper, something like that. And from there, measure out 60 degrees. Use a ruler or use your fingers to kind of pinch out the measurement of how far is that point away from our center of rotation, and then move on up and mark out that same distance along this new dotted line.
I think this is wrong.
You could continue to do more points, and doing more points could be helpful, but you don't need any more points. At this time, we have enough information to be able to draw this. Now, it definitely takes a little bit of kind of thought, some trial and error. Pencils are really good for this assignment as opposed to pens. Because what we want to do is now redraw in our figure, which if you're using the same as me, redraw in this puzzle piece so that those 2 points are in appropriate locations. So I need that to be on the edge here, down.
This is not.
Okay, back.
And I get my puzzle piece. Should be exactly the same shape. Okay, mine looks a little bit, more rounded out here than it did before. Should be exactly the same size. It's just turned around our center by an angle of 60 degrees. So it took that puzzle piece and it twisted it. Yours is much larger than it used to be. So they should be the same size. They should be the same shape. It should just be a twisting of our original figure. Right? This is the most difficult to draw, especially when we're not actually taking accurate measures and using protractors and whatnot. If we do that, it becomes a lot easier to draw in our figure. And the more points on your figure that you do would actually make this easier as well. Like if I would have marked out, instead of just doing 2 of the points on my original figure, if I would have done this for like 4 points on my original figure, that would give me a lot better idea of how to kind of connect around and create the best copy of my figure that way. Yeah. Our third type of transformation that we're going to talk about today is called a flip. To make a flip. A flip takes something and it turns it over. Its more mathematical name is a reflection. A flip is behaving like a mirror. We only need one thing for this. We need a line that we are going to flip something over. An example would say, reflect the figure over the line. And then we need a figure. Once again, you should not do something that is the same on all of its sides.
Can we do like a triangle?
That's supposed to be.
It would be much easier, but we wouldn't be able to tell whether you had accurately done it.
Can I do a triangle?
Because copying a square exactly is the same thing as flipping over a square. So if I can't tell that you've actually flipped it, it will be wrong. So we need something that's distinct on all of its sides so we can tell that it is actually done appropriately.
Couldn't you do it now?
A non-equilateral triangle would work.
Like that?
Non-isosceles triangle, then you would need a scalene triangle. And then we need a line to reflect it over. The easiest way to kind of cheat this, and I'm actually okay with you doing this, but to do this without taking any measurements would be to think about kind of drawing your figure in with a heavy writing utensil, so some sort of a marker drawn heavily, or a pen drawn really heavily, or even a pencil if you draw it out really heavily, and fold your paper and kind of press it together, and the image it would leave on the other side of that line would be the reflection. When that happened mathematically, the distance from that line should be the same on each side. So if I'm going to do this without really folding my paper, because I can't fold the whiteboard and I can't fold my iPad in half, what I need to do is think about how far is this point of the triangle away from that line and go out that same distance across onto the other side of the line. So I'm going to take this point of the triangle and just kind of measure that out over to the other side. Then I want to recreate my figure exactly the same. So how long is the bottom of this? Well, again, I could do kind of a finger pinch measurement to figure out how long is the bottom of this, so I make sure that I'm maintaining the size of my figure. But if you would draw with a heavy writing utensil and fold your paper right along that line, then the image it would leave on the other side of that fold would be the perfect reflection.
Sounds like more work.
A dilation, how it works is it is going to be the same shape, but a different size. For the other three, the more kind of colloquial name was given, and then here under the other name we gave the more mathematically correct name. Dilate is actually the more mathematically correct name. Where have you heard the word dilate before? In your eyes. So you go to the eye doctor and they dilate your pupils, which means that they do what to them? They make them bigger. When they dilate your pupils, they're making them bigger so that they can see into your eye better to see what's going on inside of your eyeball. A dilation is a growth or a shrink. Okay, it applies to both, that we could grow or shrink an object through a dilation. When they're talking about your pupils, they're just talking about growing your pupils so you can see into your eye better. Which they never have to do with me because I have abnormally large pupils. I basically live my life dilated. To do this, all we need is a growth factor. So an example, let's say dilate the figure and then give us a growth factor. We're going to do this times 2. Need a figure.
Could you use a regular figure for this because
You could.
I'm tired of these irregular figures. Just make a square.
When we do a dilation, it maintains the shape of the object in terms of the angles of the object. So I'm not changing the size of the angles. So my house has right angles here at its bottom. When I blow this thing up, it will also still have right angles at its bottom. Think of it kind of like a blueprint. Okay? But what's going to change is the length of the sides. So again, you could use a ruler or you could kind of finger pinch measurement and measure out how big this new side is going to be in that way. But the new side should be twice as big as the old sides. Okay, so a dilation is kind of like a blueprint idea here. The figure maintains its shape, and the essence of the shape, but the size of it will change. We can dilate to grow or to shrink. If our growth factor is larger than 1, that will cause our figure to grow. If the growth factor is smaller than 1, like if it said dilate by a half, then we're actually shrinking our figure because we're making everything half as big as it used to be.
Did you make it double as wide?
Yes, double as tall and double as wide. All lengths are doubled.
Can we do it like outside of it, like that?
It should be a completely separate figure.
This one doesn't.
So we looked at 4 different kinds of transformations. What was different about this one than the other 3?
You could use regular shapes.
Yes. What was different about this last one we looked at than the other 3?
It's easier.
I would agree with that.
Change the size. In all of the other ones, your result should be exactly the same figure as it was before. So like I could take a physical object and I could actually do those things to it. I could move it to a new location. I could flip it upside down. I could turn it around. I could actually do that with a physical object. Whereas this one, it changed the size of it. So I can't take a physical object and just have it get twice as big. Okay? So some objects, yes, you could do that with. But I'm thinking like I'm holding a puzzle piece. I can't make that puzzle piece twice as big. Right? But I could turn it. I could flip it. I could slide it. The first 3 of them, the slide, the turn, and the flip, are called isometries, which means they create a congruent figure. Okay? Isometries create a congruent figure. The last one we looked at, the dilation, produces a new shape that is not congruent to the original, but a different word that we learned a while ago back in chapter 7. Similar. A similar figure has the same essence of the shape, but it is larger or smaller than it used to be. So the first 3 are isometries, and the dilation is different in that it doesn't make a congruent figure, it just makes a similar figure. So again, your homework for this lesson is at the very end of the packet, the very last pages, which tomorrow, Monday, you will rip off to hand in.